Is anything going on this morning that I don't know about? Nobody else is here?
This is probably your last week.
Yeah,
in
today and Thursday is the last.
lecture, right?
Yeah.
Okay. So for next week, they will start doing the presentation.
Presentations.
I see.
Maybe. If you can record some of them also, might not be bad.
Sure.
Yeah.
I'll just put it here. So for the APS week,
Yeah.
for that 2 lecture, is that have a very good connection between your previous lecture and your lecture from the year before? I mean,
I think so.
16, 17, that 2 lectures. Can
I
I
guess I
just,
didn't make you part of the course website, but you can see it.
okay.
I can tell you which lectures I
Okay.
asked them to look at.
Okay.
Yeah.
I want to upload as a whole
As a
lecture.
whole package?
Whole
Yeah,
package.
okay. Yeah, I'll tell you which lectures I uploaded
Okay.
or I asked them to view.
Okay.
And I think it was like lecture 22, 23 or 23, 24, I can't remember. I'll tell you
Okay.
from last time. So,
For the
I asked-
APS week, I
Yeah.
think it's 16, 17. Last.
oh, maybe I can't remember.
Okay. I see.
I'll let you know. I had to look up my course web
Okay.
notes because that's how I sent them the announcement.
Sure. And also, this time, can you provide all the lecture notes, like assignment and answers?
Yeah, they're all in course web.
Okay.
Yeah.
I cannot access.
Yeah,
them.
you can access that. Right.
Yeah.
I'll just add you to it.
Okay.
That'll be the easiest, I think.
Okay.
Yeah.
Sure.
Okay, I have to get started. So here are our homeworks graded, and after the class maybe you can take them. The solutions also to most of the homeworks are on the courseware too. If you can do me a favor and look through your grades on courseware and make sure that I've correctly transferred your homework grades into the courseware. So just please confirm that. And if you're missing any homework grades, maybe there is a homework somewhere that you submitted either by somewhere in the mailbox and it has somehow not gotten to me, then I can still give you the option of turning in a homework. Even though the solutions are out, just turn in your homework and I'll give you some partial credit if you didn't turn in any homeworks before this. So yeah, so just make sure that you check your homework grades, and if you're missing any homework grades, let me know, and we can maybe try to organize some partial credit on those. So that's number one. I was just telling them you can take the graded homeworks after class. So once you check your homework grades, and just contact me if there's any missing homeworks, and look through your homework grades here and make sure there are no mistakes in my grading and so on and so forth. So the other thing I wanted to again remind you is I only heard from one of you about topics for the final project next week. Only one person, Shinny, you're the only one who has responded to me. So please by today, send me an email about which final project topic you're taking. And secondly, I might try to compress it because I think we have PQI also starting next week, which I had forgotten about. And so originally the plan was to do it over 2 days, Tuesday and Thursday. I'm trying to see if maybe we can just do it in one block on Tuesday or something like that. So maybe we'll shorten the talks from, I think right now I said 20 minutes. So maybe we make it 15 minutes per person. So do plan for 12 minutes of talk and 3 minutes of questions or something like that. I'll send out an announcement about this so that we can try to compress it into 2 hours or 3 hours at most and get it done with on Tuesday if possible. Which means that everybody will not be ready on Tuesday. So you can't relax till Thursday like before.
Is the presentation in the finals week?
Yeah. I'll find a room.
But PQI is next week.
Yeah.
It doesn't conflict.
No, next week is finals week.
What? No. The week after next week is the final week.
Oh, really?
Yeah,
You guys seem to have a wrong calendar somewhere then. I'm sorry.
Today's 8.
I looked it up on the PIT website.
Next week is 15th.
Yeah.
And the week after is 20th.
Is 22nd is the last week?
Yeah.
Is the finals week?
Yeah.
Oh, so we have one whole more week of classes?
Yeah.
Oh, great. I've been hurrying to try and finish up all our... Oh, this is great. I can give one more lecture. Sorry. Okay. Now I had to rethink my whole plan. I've got to go back and check. Something must be wrong in my calendar. Like I normally have it downloaded. Maybe there's a problem with the Google Calendar or something like that. Okay, I'll recheck. Thank you. So you're saying next week is the last week of classes, not finals week. And then final week is the week after that. Oh, okay. Great. Fantastic. Which means I can go a little bit slower and maybe even introduce one more lecture on quantum information perhaps. Or quantum optics. I'll let you guys decide which one you prefer. But. Okay, so that's about, so I better rethink my whole strategy for next week. I've been thinking that I need to rush and finish all this next week. Okay, so was there something else I wanted to say? Okay, no wonder you guys have been relaxed about presentations. I guess you thought you had more time. I was thinking, why is no one responding to me if it's next week? So you guys have been thinking, oh, it's 2 weeks from now, I have lots of time. But I think it's still good that you respond to me with your presentation topic, which is today, okay? We don't want to keep waiting till the last minute. Okay, all right, so let's keep going then. We had started Simon's algorithm last week. I will just recap what the problem was and then discuss it. So in Simon's algorithm, the problem that Simon was considering is that there is a function f of x which is equal to f of y if and only if x equals y plus a, okay, where a is the period for the function f, okay, and so x is typically belonging to some n-bit strings, binary strings. You're familiar with this, and y is typically belonging, and f of x is typically belonging to some 0, 1 to the m number of bits. Okay? I mean, what we're saying is we encode the answers f of x into some bit strings because not all of the values of f of x might be unique. In fact, we know they're not unique. F of x equals f of y for some period. So there's at least one less, sort of bit needed. And I gave an example in the last class where I said, suppose imagine f of x is some musical symphony, right? And what it does is for every bit string, it assigns a note of the piano or the guitar, which is my favorite instrument, but choose your own favorite instrument. Maybe you like Indian music, then you choose some other songs, some other notes in Indian music, or you like Chinese music. I don't know what the notes are in Chinese music. How do you call the notes in Chinese music? I don't know. I know only the Western music, A, the standard A, B, C, D, and E, and F and G. So those are the standard notes of Western music. So whatever the notes are, for example, in the last class, I gave a sort of like a simple example of like a periodicity where the notes repeat after some period A, which you have chosen A, and the output, which are the notes of the symphony, can be encoded by a 2-bit string. Okay, because there were 4 distinct notes in the symphony, and there were 8 possibilities for the input, and there were 4 distinct notes in the symphony, and then we just encoded the notes of the symphony with 2-bit strings. Okay. And so we said that so n equal to 3, m equal to 2, and then we had some period for the symphony, and the aim was how do you find this period for the symphony f of x. Okay. All right. So to do that, we started with the first step of Simon's algorithm. And I also showed you in the last class that if there are capital M values of of the xi in the classical algorithm, all you can do is pick some values of xi, and let's say you pick some capital M or capital R or whatever values of xi, then at best you can get eliminate at most r times r minus 1 over 2, that is r choose 2 number of these pairs of these xi, because you just have to search for the period of this unknown function, the simple. Okay, that was in the last class I showed that result, and from that we know that then this problem will grow exponentially with the size of the number of the bit strings. Or okay, so because there are 2 to the n minus 1 values of x, and therefore you'll end up having to at least look at square root of that number to find, because you know the size of your solution space goes as like r squared, the size of the total space is n squared, and therefore you 2 to the n, therefore you have to choose at least 2 to the n over 2 values of the total number of pairs classically. So classically need at least m on the order of 2 to the n over 2 values prior to success. Okay? And therefore this is an exponential growth in the size of the algorithm. And what we will now show is with Simon's algorithm that this will happen much faster. It will happen on the order of n times, which is an exponential speedup. So Simon's algorithm, as I mentioned to you last class, we give it a simple sort of mnemonic to remember how to do these algorithms, which is first you rotate. Okay, and I started showing you this in the sort of the circuit diagram picture. So let me draw again the circuit diagram. So this is x. It goes from zeros, which are encoding in zeros at the beginning, right? There are n of them, or n qubits. And then we apply our famous Hadamard and gate, which is just, of course, individual Hadamards on each qubit. Okay? And when we do that, we looked at the output. So this is time step 1, time step 2. At time step 2, we showed the output of the circuit is simply the uniform superposition. And I should also mention, remember we have always said, we also have the ancillary qubits, which are where the answers are going to come out, which I call the Y qubits, which is 0, also initialized in the state 0, and there are m of them. Okay. For now, we don't do anything with these. We just let them go through. Okay. And at time step 2, then, the state of the system psi is going to be h in times the unitary operator 1 on the Y qubits. So we have 0n and 0m. And this is, we already showed this before, is just the uniform superposition of all the strings in the, where now I use a slightly different notation for 2 to the n minus 1, or maybe I'll write it again, n equals 2 to the n. Okay, so that is the total number of n equals 2 to the n. That's 0 of the n. Okay, and so this I could also written as 1 over square root of n, because that makes it look like a nice simple averaging, and then this is xn 0m. So after the first part of the circuit, we have achieved a uniform superposition of all the input states, which is nice because, as I described to you before, that is the so-called massive parallelism of quantum computing. Okay? At time step, after the time step 2, I apply our quantum circuit that implements the function f, because as I said before, the quantum circuit f, any classical circuit f of x can be applied again in the I just want to make sure I use the same notation. So this is, I used UF over here, which represents the unitary quantum circuit that that we are going to apply to the to this qubits to get the answer in these qubits. Okay. That's what UF is capable of doing. It evaluates the function f of x on all of these qubits and puts the answers in the M ancilla or answer or output qubits. Okay. So at time step, let's say 3 over here, let's write the state of the system, which is UF H n cross 1 Okay. Now, the last time I explained that what we're going to do here is measure the output answers. Okay? And I'll get some collapse of the entire system into some measurement result on the answers. Okay? Let's call that measurement result, and if I want, I can call this time step 4, which is author measurements. Okay? This measurement is going to collapse the result onto some values, f of x naught. Okay? And when we do that, we know that there are only two possible values of x, because remember x, well, there could be more, but we already showed because of bitwise addition that if x and y are related through this notation, then any other shift by the value a gives back the same value. So meaning there are of course multiple other values because the bit strings would be enormously large, 2 to the n of them, and if say your period is small, for example, then you could have many answers, but it doesn't matter because we'll get the bit shift x equal to y. So for example, if x equal to y plus a, then this is the same as x equal to y plus is equal to x equal to y, right? For example, because a plus a by itself must also give you back the same answer. Okay. Okay. So and this was the trick that we were coming to now, which is once we have measured this, that means that the input over here 4, at this point the state of the system has reduced to very simply this system over here, and let's call this f of x naught as some, since we were choosing some musical note, some string, let's say some S naught, okay, which is the answer, just the answer for the measurement result. Great. So right here we have the answer, right? If we could get x naught and x naught plus a from here, if we could read out which of these it was, if we could read each of these amplitudes, x naught and x naught plus a, we could calculate a. Just by taking x naught plus a will give me the answer a. But the problem, as I explained to you, is if I measure this, the input register now, okay, the output has collapsed, we don't care about it anymore, right? We just leave it as it is. But if we take because this is unentangled, right? S naught is the same here, so you can take it out of this superposition. So we are just left with x naught plus a in this state over here. But the problem is that when I measure it, I'll get either x naught or x naught plus a for some random x naught. You say, well, okay, what else can I do? Well, run the circuit again, right? And I should get, but unfortunately, you know from quantum mechanics that you'll get, let's say you get S naught again. The problem is you may get some different values here for S naught, right? S naught would be some new value, right? And this S naught will be made up of two random numbers, x naught and x naught again, a different random number, so call it, x naught prime. So each time I run the circuit, I will get some new result. And I will be back to the problem that I had to run this circuit 2 to the n times to find all of these measurement results. Maybe I reduced by a factor of 2, I'm not even sure of that. But, so it's no good, right? At this point, we have not achieved a speed up of the system. This is when I said we are going to do a trick, which is we are going to again apply Hadamard to the end. And this is what Simon mentioned as his algorithm, which is rotate. This is rotate. This is compute. It needs no explanation. You compute the function. You have to, of course, build the equivalent quantum circuit that implements the function that you want, and then rotate again. Okay, so just remember this sort of algorithm in quantum computing, which is very common. Plus, of course, you may do some measurements somewhere. Okay? And in your homework problem, I'll even, I think I mentioned this when I taught the no cloning theorem. Today I'll assign some more homework problems. And at first I was going to make them somewhat optional because I thought we were out of time, but the people here have reminded me that we have time for one more week of classes, therefore one more week of homework for you guys. But but the homework, I don't think it's, crazy hard or anything like that. What I will explain in that homework was, for example, in the proof of the no cloning theorem, we had assumed that all the operations were unitary, and we showed that then, if the operation is unitary, then there's no way to build a quantum cloner. But one of the questions I didn't address is what if the operation is not unitary? Then maybe can I build a quantum cloner? And that's one of the sort of the results that you see. Similarly, which is called the principle of deferred measurement, meaning it means that even if I build some circuit with measurements in it, I can always rewrite it as a unitary followed by measurements, okay? At the end, like not having to do the measurements in the middle of the circuit. So we can always recover that sort of this kind of rotate, compute, rotate, maybe with some measure in any circuit or any function that you want to build can always be made into this kind of paradigm of this kind of framework that works. And so now we can answer the question, what happens? So, okay, so suppose I now apply this final part of the circuit. Let me write it over here. We have to find what is the action of h to the n now, not on the set 0, 0, 0, but on the set xn, where x is some random string, right? X can be any string in the entire 2 to the n number of strings. So h n acting on x naught, okay, is what? This is what we have to answer this question. So last class I tried to show it by example, but I think I did a bad job. So let me try to give you an example which is maybe hopefully a little bit better. Okay. So let's consider 3 qubits. and let's just pick some string 1 1 0. Okay, and once we do this example, I think then for the n qubit case, I gave you the answer in the last one. Just by general principles, you can write down an answer, but I thought it's useful to do the example. Okay, remember that H acting on the state 1 is just the state minus. Remember, I've told you what minus is. It's 0 minus 1. And then acting on the state 1 again is minus. Acting on the state 0 is the state plus. Okay, this is what I was trying to get to last time, but I didn't do it very well. Okay, so, and in fact, I can just write this as, you know, if I have different colored chalk, maybe it would be a little easier to see. Use is minus, minus, plus. Okay, we'll write it like that, just to say that, you know, that's the state. Okay, and now we have to write it out. So it's 1 over root 8, 0 minus 1, 0 minus 1, and then 0 plus 1. Okay? Which is, as you can immediately see, is 1 over root 8 summation of all the possible 3-bit strings. Because this will give you 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, etc. All of these patterns, all the possible, again, 8-bit strings. So call them some S belonging to 0, 1, 3, which represents all the possible 8-bit strings, S, okay, with some pattern of plus and minus. Okay, it will be plus to the power whatever is, of course, plus, or minus whenever there is a minus sign. And the pattern is what we are trying to find out. Okay, this pattern, this question mark here represents some pattern of pluses and minuses. Okay, and of course we can write down the answer for this unique case. It's very straightforward. We want to write it in such a way that the answer will be obvious for the n-bit case. Okay, or any arbitrary x. Oh, I cannot erase this. This is so beautiful. Let me write it. I'll leave it up there. And qubits. This is x. This is y. Okay, I'll leave that there, right? Alright, so that's our circuit. I'll proceed with the proof over here. Remember that this was the final result, and we are now trying to apply the Hadamard, say, for this n-bit operator over here. What is the pattern of plus and minus? It's pretty easy to see. Okay, so let's consider. So in this case, the x is equal to 1 1 0, or x naught is equal to 1 1 0. And what is the sign on s? Okay, so if the sign, if s is 0 0 0, then the sign is plus plus plus, as you can immediately see, right? Plus plus plus. Okay, so the answer must be plus. If s is 0 0 1, okay, then the answer is also plus plus plus, because x was equal to 1 1 0. Okay, you can verify that immediately, right? 0 0 1, all three are pluses over here. Okay. Now look at the state 0 1 0. Okay, the answer is plus minus plus. So this is also plus. So the answer is a minus. Proceeding to the state 1 1 1, the answer is minus minus plus. So the answer is true. Okay. And the reason for that, I'll have to erase this. Just remember that this was the answer that we are trying to examine now. So if you look at the state S, right? If Si equal to 0, if let's take one of the bits in this string, right? There are 3 bits in this string, okay? If SI is 0, the sign is always plus for that particular bit. If SI is 1, the sign is minus if the corresponding bit over here is also 1. Okay? Look at the pattern over here. It's only minus for that particular bit if the corresponding bit over here is also 1. Check the pattern that I wrote. Okay, if you have convinced yourself of that, then, so in general then we can write the answer for S is the product of all the signs for SI, okay, I equal to 1 to n, where if SI equal to 0, the sign is always plus, and if SI equal to 1, the sign is minus if XI equal to 1. If and only if. Therefore, the pattern of those plus and minus is the product of all the signs where SI equal to 1, okay, minus 1 to the power XI. What does that sound? Which means this I can write as minus 1. Now, because it's a product of exponents, I can write it as minus 1 to the power summation of I such that SI equal to 1. Again, of XI. Then of course I had to put, when I do modulo summation, I had to put modulo 2, okay? Which is the same as saying that this is the minus 1 to the power S dot X, where I introduced that this S dot X last time is simply the summation I equal to 1 up to whatever SI, XI, modulo 2. Okay? So that is the answer, and I hope that it is the same answer that I derived last time, but I hope this way of deriving it for a simple example first, hopefully can convince you that that answer is correct. Okay? Or is at least more intuitive than just finding the answer. In fact, there's a nice way to look at this, which is that the pattern of that minus signs, which is over there, this function S dot X, remember, is also like the XOR function, okay? Because basically if I write out this S dot X, is S1 or S0 X0 plus S1 X1 plus Sn minus 1 X n minus 1, right? That is the pattern of these bits. So this is given the name, say, XOR of S of X. Okay? Because it takes the XOR of X, of the bits X, where Si equal to 1. Okay. Only if Si equal to 1 will that part of the bit be counted in this sum. When XOR is not equal, when Si is 0, that term will drop out of the sum. Okay? And when Si is equal to 1, that term will be included in the sum. Okay? Okay. Furthermore, so this XOR S of X, there's just a little bit of math, magic or obvious, corollaries of this. So this is I SI equal to 1, I such that SI equal to 1. I belonging to the set SI equal to 1, if you like, is equal to XI mod 2, right? Which is the same, just rewriting of the same equation over here, which again I write as I equal to 1 to n SI XI modulo 2. Again, just the same equation that I wrote up there, okay? Which is symmetric in S and X. So this is the sum over Xi equal to 1, Xi such that Xi equal to 1 of Si modulo 2. Okay? Which means that this is the same as the XOR function for X of S. Okay? This is just a notation which might be useful because what it shows you is that this Hadamard transform that we had written earlier, which is this Hn, basically looks like it's creating some kind of pattern of the inputs X, which is governed by this S, the answer that we are looking for. So it provides some pattern of those bits. It's not exactly the bits themselves, but it provides a pattern of bits. And the pattern is governed by a function. And the function is something that we all know from digital logic, this XOR function. Okay? This is going to be an important viewpoint as I'll try to explain it when we go to other kinds of functions. Okay? If I view this XOR as a function, then you'll begin to see how you can generalize this to other functions. In fact, the function that is useful for factoring. Okay? In the next part of the class. Okay? So the corollary then is that we can also write Hn of S equal to 1 over root n sum over all x 0 1 n minus 1 XOR of S of x of x. Okay? And furthermore, H is its own inverse, so H cross n to the whole inverse is the same as H cross n. So we can carry that H cross n over to the other side, and H cross n acting on that whole superposition, 1 over root n minus 1 XOR S of x, summation x, I'm not writing all the terms again, x is equal to s. Okay, so that is our final sort of result for all of the things that the Hadamard transform does on the bit pattern. Now let's go back to our algorithm. Okay, Hn acting on x0 plus x0 over here. Okay. So now Hn is now acting on the superposition 1 over root 2 x0 plus x0 plus a. Remember? That's where we were at time step 4, and we applied the Hadamard transform now on this set of qubits. And that gives me an answer which I can write without further ado. 1 over root n, 1 over root 2 times summation y equals 0 up to 2 to the n minus 1. Let's stick with, since I used, I guess I shouldn't have used s there. I should have used y, but you can just carry it over all the results. N minus 1. Okay. Minus 1 to the x0 times y plus minus 1 to the x0 plus a times y times y. And of course, again, I remind you that on the answer over here, there is some answer of the particular answer, which is, let's call that some R0. Okay. Results. Okay. That is the answer that corresponds to this particular value, f of x naught. Okay. So this is the answer on the input registers now. So look at that. So the particular values of A that we want are somehow encoded now in the input registers after the Hadamard transform in the sign of these -1 patterns that we have written over here. And remember, originally we wanted to take the XOR of that values. If you would have directly taken the XOR between x0 and x0 plus A, right, then we would have gotten the answer A. So we haven't directly taken that function and XORed the values, but now we have them stored in the powers of this x0. Okay? So let's proceed to understand this. Okay? Means, now, so -1 to the x0 plus A times y is equal to -1 to the x0 times y times -1 to the A dot y. Right? Just addition in the exponents is equal to the product of these two. Okay? And -1 to the A dot y will be equal to -1 if A dot y equal to 1 and plus 1 if A dot y equal to 0. Okay? So the coefficient in front of this superposition over here the coefficient of y, one of the terms in that superposition, is either 2 times -1 to the x0 dotted with y if A dot y equal to 0 and 0 if A dot y equal to 1. So we can finally summarize our answer. H cross n on 1 over root 2 x0 plus x0 plus A is equal to 1 over root 2n, okay, times summation A dot y equal to 0 minus 1 to the x0 dotted with y times, okay. So the sum will be only over those values of y such that A dot y equal to 0. Okay? Okay, how is this helpful, you are wondering? Well, now we measure the input register. Okay? If you measure the input register, sorry, I don't have space here, but imagine that I now put measurement at this point. Okay? So now measure. Okay? Now I measure the input register. Each time I measure, right, I'll get some random answer, y, but I'll get, therefore, some set of A, if you want, I'll even write this as a sort of, form that maybe you'll be able to understand. Each time I measure, let's say I measure n times, okay? Okay? I'll get some y's, okay? Y, some values. I'll get some values of A times y, which is 0. Each time I repeat the measurement, I get this. I may get different values of the y's over here. That's fine. Okay? But basically I'll have a set of equations, okay, where a times one of the bits in that equation is equal to 0. Okay, the sum of those is equal to 0. Okay, so that if I want, I can write this as implies summation I equal to 0 n minus 1 yi ai is modulo 2 is equal to 0. So each time I make this measurement, I get an equation, a linear equation. Okay, I get n of them. I can solve for all the bits in it. Okay, so that is our algorithm for Simon's algorithm. And as you can see, I have to do this n times. Okay, because I need n equations to find every bit of it. Okay, and so this is the exponential speed up of Simon's algorithm. Okay, because instead in the old algorithm there are 2 to the power n. Now I need only n calls to the circuit and measurements, and I get the answer for A. Okay. So this is the first example of a quantum algorithm that provided the exponential speed up for a task. Once again, I should mention this task is somewhat artificial, right? We have this. I mean, I set it up as this beautiful musical symphony and so on, but you know, of course, in real life, there are not many examples like this where you need to find some hidden periodicity in this particular set of regions. Okay, but this will immediately allow us to generalize to Shor's algorithm. Okay, we'll see Shor's algorithm in the very next moment. Okay. Before we go to Shor's algorithm, I had to introduce quantum Fourier transform. But that's basically the answer. Okay. Okay. So at this point, the answer is there, right? We already have the answer. So I'm not going to explain. You know, you could think of it. Sorry, I made one. The way you want to write this, the A's are the ones that are unknowns that we are solving. Right? So A 0 up to A n minus 1. This is what you're looking for, and each run gives you some y, or 1, y of 2. So those are the ones that you're getting from the inputs, the y, and the unknown is the A0 up to A n minus 1. It's the other way around, not the way that I had it. Y is not the unknown. Y is the result, right? And then A's are the unknowns. So, sorry. But the basic idea is the same, okay? I just mislabeled things in the previous matrix. Okay, so, and of course I can tell you about analyzing the speed of this algorithm. I'm not going to do that. You know, it's I've just said it's n times. You can ask what is the probability that how long or how many calls will you need? You need, I said, on the order of n. It turns out you need on the order of n plus 20 more calls if you want roughly, say, an error probability of 10 to the minus 6 of finding the right answer. Okay, so it's not quite n. It's n plus some constant overhead to find the right answer. Okay, so because of course these are some random bits, so you might have some problems there. And, you know, what if some of them turn out to be the same? Then you have to repeat, and so on and so forth. So those are the only sort of errors that can creep into the algorithm, and we have to address that in this error consideration. So just to summarize them. So this is the quantum part essentially of the algorithm. And then the rest of it is just calculating errors. So I'll just say that without proof, with n plus x runs of algorithm, error probability, probability of success Q becomes greater than 1 minus 1 over 2 to the x plus 1. And if you're interested, you can look at Mermin for the proof of this result. So as I said, if x, so maybe I should use not x. X is already being overloaded. So call it R. So if R on the order of 20, then this becomes 1 minus Q becomes 1. Okay. Any questions about Simon's algorithm and the result? Okay, if not, then I'll put all these notes up. I was having some problems with my computer, with my iPad. I couldn't quite upload it, but I think I fixed it this morning. So I'll upload last week's lecture also on Simon's. Okay, so we've done Simon's algorithm and sort of remember this idea: rotate with h to the n, apply the circuit UF, and then apply another rotation. And that is the paradigm of Simon's algorithm. What we'll see with Shor's algorithm is very similar. Rotate, and then there's a compute part, which is a little bit more complicated. And then instead of this Hadamard transform, as I call it, it's a transform because at this point now this is a uniform superposition of many different results. Instead of this transform, we'll apply something called the quantum Fourier transform. Okay? And that is what I will introduce now next. Okay. This part will remain the same because we always, as I've said, in quantum computing, we always want to start with uniform superposition of all possible inputs to the quantum computer, and that requires this initial h to the n. So that is, we think of it as just preparing some uniform superposition at step 2. Then we apply our compute circuit, and of course in Shor's algorithm, it will turn out that this compute circuit requires a certain number of quantum gates. That actually turns out to be, usually in all these algorithms, both Simon's algorithm or Shor's algorithm. So in Simon's algorithm, we are assuming this UF is just given to us. Some black box, somebody built the quantum circuit, and we're just trying to use it, right? Of course, for Shor's algorithm, if you ever want to implement it, which is the most useful sort of quantum algorithm right now, is the quantum factoring algorithm. As far as people in cryptography are very interested in using it because just to back up. Does everybody know why Shor's algorithm is so important? I don't know if I talked about it enough yet. Okay, so I can give an introduction, or maybe one of you can talk about it. But I'll come back to that in the sort of the number theory and all those aspects of it. But the basic reason is, as you probably all know by now, all of our e-commerce, everything from your bank transactions, your email. Name anything you want, like your photos, Facebook, whatever, everything is protected by a certain type of security on the web, right? You might have noticed in your browser, there'll be a little lock icon, right? And the lock icon, what is it doing? How are people, making sure that whatever you send over the internet is not being intercepted by someone and just read, okay? Anybody could have read your password, your emails, your e-commerce, of course. That's every day about $2 trillion is happening on e-commerce websites, okay, around the world. Okay, so imagine the amount of money that somebody could make if they could crack those transactions. Now, when you think about national security for any country, the way all the documents are being encrypted and stored, very very important documents. This is also stored via some kind of encryption. Okay, where is this encryption coming from? This comes from a group of mathematical results, which is called one-way type of mathematical functions. Okay, and the example of this, the very famous example, which is the classic example, and this is what is being used in most of the encryptions, is factoring. Okay, so you all know multiplying is very easy, right? You've all learned it in multiplying two numbers together is very simple. Okay. You just take those two numbers and you can implement a very simple algorithm yourself to multiply those two numbers. Okay? So if I have two large numbers, and when I say large here, I'm thinking 2000 bit, let's say. Okay? So 2000 bit seems large, but when you break it up into number of bytes, it's not even that big as a number itself. Okay? Because, anyway, so I'll come back to all these considerations later on. But if you take two 2000 bit numbers and multiply them together, nowadays with chips that we have, this can be done in less than a microsecond or something like that. That's even too long, because when you think about like the types of, in your PlayStation or your Xbox, if you have one, then in those itself, each of them can do like a floating point operations in 10 to the minus 12 seconds. Okay, one floating point operation or one multiplication can be done in 10 to the minus 12 seconds. Okay? And each floating point number is typically stored as say 2 bytes. That's already 32 bits. Okay, I'm sorry, 4 bytes. So that's already 32 bits right there. Okay, so a 2000 bit number sounds big, right? Because we know it's very big, right? 2000 bits. That's any number from 0 up to 2 to the 2000 minus 1, right? Can already be done using floating point operations. Multiplication can be done in like extremely fast time. You can easily work out, right? 10 to the minus 12 second is 1 picosecond, right? So like imagine you can do this all in like less than a microsecond easily, okay? This multiplication. But the inverse problem, which is factoring, if I give you an answer which is the product of two such large numbers and tell you find me the two numbers that originally created this number, okay? That is an exponentially hard problem. Okay, this is what we mean by one-way one-way functions, or the inverse problem is very hard. Okay, the forward direction is easy, the inverse direction is very hard. Okay, and if you plot the graphs of these, and maybe what I'll do is I'll make sure to download that slide, the graph from one of these famous papers, and show it to you on my computer. Which will show you that the growth is so large. Like for example, like if you went from 1000 bits to 2000 bits, right? The factoring becomes like on the order of like 1 billion years. Like so, it'll take 1 billion years to factor with currently known classical methods a 2000 bit number that has been created by the product of two, say, 2000 bit numbers. Okay, and all you have to do to make this problem even harder is just increase the number of bits a little bit, okay? Right? Every time you add 1 bit, you double sort of the difficulty of the problem, okay? The space of possible answers is doubled, okay? And so that's a huge growth in the number of answers. So this factoring then is being used by all the encryption software to encode your answer. So basically what they do, the simple version, I just explain very briefly. Let's say you write some email or you have some bank transaction and you want to send that information, or your credit card number, for example, right? It's obvious. We are all buying stuff with the credit card online nowadays. So you enter into Amazon your credit card number and it just charges it, and nobody else hopefully can get access to that. The way it does it is it takes your credit card number, it XORs that, the credit card number is just some bit string, it XORs that with a secret key. Okay? And the secret key is basically being created by the product of these two prime factors. Okay? These factors are usually chosen to be prime numbers as well. Okay? So these two prime factors are chosen, they are multiplied together, and then the answer is then taken and XORed with the bits that represent your credit card number. This encrypts the numbers, sends them over there, and then you have to ask how do you decode over there. That's a separate step I can explain. But the problem for anyone who's trying to find out your number is now they can see the numbers, right? They can see all the numbers on the web, okay? And but the problem is that they don't know the secret key that was created, okay? The secret key which was used to XOR your original credit card number, if they could get that secret key, right? Then they would be able to factor that number. So I've given a very vague overview, hand-waving overview of this. I'll come back and explain to you in more detail how this is done. Okay? But today, what we're going to simply do is extend everything we did with these bit strings out to a different set, which is the quantum Fourier transform. Okay? And so let me explain the quantum Fourier transform, and then we'll understand the way in which Shor's algorithm works. Okay. So in this Shor's algorithm, we've already seen now. So we already showed in Simon's algorithm, h cross n x is some 1 over square root to n. Okay. 1 over square root of n. Summation s equal to 0 up to n minus 1 minus 1 to the x to the s times s, right? This is the minus 1 to the xr function. And what we are going to say is we can think of this as a Boolean Fourier transform. And I'll explain what I mean in just a second. First of all, I want you to recall the mental perspective that I had asked you to take about quantum computing way back. Which is, remember, we said any number, any qubit state, C0 up to Cn minus 1, right, was represented by 0, 0, 0 up to 1, 1, 1, 1, right? Okay? And this represented the truth table of some function x with f of x, right? So x went from 0, 0, 0 up to 1, 1, 1, 1, 1, and f of x went through C1 up to Cn minus 1, right? This is just the encoding of the truth table of a function f of x into the qubit state vector, okay? Now I can erase this. Hopefully you'll always remember this, the Simon's algorithm. Well, if you do quantum computing, I suppose you should remember it. And I said the state f of x in general is nothing but the f of x acting on x, summation x equal to 0 up to n minus 1 with some normalization, okay, which I am ignoring for the time being. Okay. In fact, in this case, for any normal qubit vector, we can just take square root of it, right? So, let's call this y, the time-honored math tradition that the result of a function is always denoted by 1, right? So y, which is the function, which is the ket f of x, is simply this superposition of all the possible answers when the function f is applied to the uniform bit string created by the Hadamard superposition, okay? Well, if we now apply the Hadamard to this, right? Well, I just told you the part of that answer, right? It is 1 over root n summation x equal to 0 up to n minus 1 f of x times h to the n of x, right? And we know what this h to the n of x is. It's another summation, right? So this all looks very complicated, but if I call this as some f tilde of s, okay, and I wrote this superposition as 1 over root n summation s equal to 0 up to n minus 1 f tilde of s, okay, then you begin to see that this guy here is transforming hn acting on f of x instead, right? It looks like it's, of course, this f of s is just some coefficient, right? Because we know what exactly hn does. It creates this minus 1 to the x to the s type of pattern. And basically what it's doing is multiplying the coefficients c1 up to 3cn or f of x, which is basically f of x, by some pattern which is given by this function over here. Okay. So I'm taking the product of these two functions. This should remind you of the Fourier transform in the following way. Okay. Erasing this. Don't do this anymore. Suppose you take any data vector of length n, okay? And this n of course is 2 to the n, and remember the data vector, by that I just mean something like this, ket g let's say, belongs to C to the n, right? Or, which is this C, meaning each of these is a complex number, and so I take this ket G to be belonging to that complex number. Okay? I'm now going to take a Fourier transform of this guy, which is based on some basis. Okay? And let's say there are n of these basis vectors, and I'll call them u0 up to un minus 1. Okay? So we all know how to take Fourier transform, right? The length, but before I show you what it is, the output of that will be again a length n vector whose, say, jth entry is the strength of this G projected onto one of these basis vectors, right? The length n vector with the jth entry is the amplitude, or you can think the strength of this function or this pattern or this basis uj in the data G. So again, this is just the equivalent of what we are saying is if I take this function f of x and we Fourier transform, or we take its projection onto the pattern. So in pictures, this is in words. Let's imagine that you have some basis. This is the logical basis, say 0, 1, right? Right? So 0 and 1 is the logical basis. In some higher dimensional space, you could of course make this n bits. It will be some multiple dimensions. But now imagine I take some other basis u0, which is rotated with respect to the original basis, and I take some other u1, so this is ket 0 and ket 1, okay? And then any state psi, which normally would be written as a amplitude A times 0 plus B times 1, I can project it onto u0 and u1, and I say that j of G, where G is the ket, is the strength of uj in G. Okay. And the symbol that I have just given it is G tilde of, in this case, J is equal to this uj acting on G. Okay. If I write this entire set of amplitudes and the basis vectors in a matrix form, it will make it even more obvious. What we are doing is just a basis transformation, right? We originally had the basis u0, 0 and 1. Now we are transforming to a new basis, which is the basis with u0 up to un minus 1. So let U be the matrix whose columns are u0, u1 up to un minus 1. Okay. So U takes you from standard or logical basis, 0, 1s for example, to a new basis, u0 up to un minus 1, and its inverse, u inverse, which is the same as u dagger, right, because it's unitary, takes you from the US basis or UJ basis, whatever, back to standard basis. So if I took G in the original basis, which is the data as I think of it, right, which is loaded by taking the function f or the quantum circuit f and applying it to the uniform superposition, then by applying the transform u, okay, I take it into the basis, which is u naught acting on G, u n minus 1 acting on G, and this, so u where uj of G is the strength of the pattern, which are, remember, this pattern of u's is itself a function. It represents some function f whose truth table, remember, is something that we are interested in. For example, suppose so far the function, if I draw it out for you, it might be a little bit easier. Of the pattern, let me finish this. Of the pattern uj in, okay. So of course, one pattern that we have already seen is the Boolean Fourier transform pattern that is created by the Hadamard operation. Okay. So that is, you can think of it as an XOR pattern, and I'll just in fact write it out for you so that you'll see that it is indeed a pattern. Okay. Order of pages mixed up. What did I want to cover next? We have 2 minutes. Let me just outline the Boolean Fourier transform. So before I go on, the remark I want to make is, of course, this is a very general consideration. This is some transformation of basis vectors. Okay, you say, no big deal, I know how to do that in paper, but of course the problem is how to do this in practice, in an experiment. For the Hadamard transform, we saw that the Hadamard transform is very easy because it's one qubit case. It's just H acting on each individual qubit in the circuit gives me the Hadamard transform. Okay? And in fact, I'll show you in a bit that this is just the equivalent of a Boolean Fourier transform, okay? Which is basically we are decomposing the ket into square waves, sort of. Square waves of different duty cycles, okay? And of course, the natural question we all know from our physics classes is, instead of square waves, maybe more interesting is sine waves and cosine waves, okay? And that is the quantum Fourier transform. And of course, that would also be only mathematically interesting unless we could actually build easy circuits that will implement the quantum Fourier transform. Okay, so there are 2 parts of this quantum Fourier transform which are interesting. One is, if I adopt the perspective that this is a Fourier transform, like I was just explaining to you, this is transformation from one basis to another, and that gives you like the strength of the ket in a certain signal pattern, like a square wave or a function that has alternating +1 and -1 signs. Okay, that's the square wave function. That is one type of way to think about the Hadamard transform. The quantum transform is just nothing but the same thing applied to sines and cosines. Okay? The Hadamard transform was easy to implement. We just had 1 qubit gates and we implemented the Hadamard transform. The question is, can we implement a quantum Fourier transform in a similarly easy way? It won't be quite as easy as the Boolean transform, the Hadamard transform, but it will turn out it's still relatively easy to make. And so that's why they are so important or easy, is that in fact it's easy to make this quantum Fourier transform matrix work. Okay? So let's look at the pattern for the Hadamard transform, or the Boolean transform. So in Simon's algorithm, we implemented, let's say, h cross n, right? Let's consider n equal to 2, and I'll just write it out. H cross 2 in terms of matrix, okay? So any unitary matrix could be thought of as essentially some kind of Fourier transform, according to this general consideration. Applying it to the Hadamard, which is easy to make, let's apply it. Is equal to this matrix, which I'll just write out for you, plus 1, plus 1, plus 1, plus 1, minus 1, plus 1, minus 1, plus 1, plus 1, minus 1, minus 1, plus 1. And remember again, the trick to knowing what these columns are to look at the rows and the columns. This is the state x, which can be 0, 0, 0, 1, 1, 0, 1, 1. And the output can be thought of as encoded in the columns. This is the rows, is the input. The output is those s, which is just also 0, 0, 0, 1, 1, 0, 1, 1. And we use our old trick, which is if the input has a 0, then the output will be plus if the corresponding bit is a 0, and will be a minus 1 if the corresponding bit is a 1. Right? So you'll only get minus 1 to the power of this bit xi if the corresponding bit in si is also 1. Okay? So this will be the second bit over here and the product of all of them. Okay? So if it's 0, 0, okay, that's obviously going to be a plus sign, and if it's a 1 here, this will be minus 1 to the 1 if the corresponding bit in s is also 1. So this is indeed a minus 1. Okay? Same thing over here. The first one is a 1, but the corresponding bit over here is 0. So that's just going to give me a plus sign. Okay? The corresponding bit here is 0, and that one is also is 1, but the bit over here is 0, so that's minus 1. That's just going to give me a plus 1. Okay? Again, because there's no minus 1 needed over there. And the same thing over here, both of these bits are 1. This should be raised to the minus 1 power, but this guy is a 0, so that one is just a plus. And then this one is a 1, so that one gives me a minus 1 over here. So this is the trick of knowing the pattern. So if I plot these patterns, just very quickly, it's pretty obvious, right? This looks like a square wave. Okay? So if I plot the numbers, when I say square wave, here is x on the x-axis, as always, and here is u0, which is this first column vector of the matrix. Okay? And that number is indeed plus 1, right? Plus 1, plus 1, and plus 1. Okay? So this is plus 1 for each of the values 0, 1, 2, 3. Okay? Because the x-axis is indeed the number 0, 1, 2, 3, represented by each of these bit strings. What about the pattern U1? That is simply the alternating pattern. Okay? And you can carry out the same. So this looks like square waves of different duty cycles. Okay? Within, of course, this small world, a discrete world. Okay, it's not a continuous world that we're used to in physics. It's a discrete world. Okay, where each of the x-axis points is just a simple number or an integer rather than a rational, real number. Okay. Okay. In the next class, obviously the extension to this is to consider sine waves. Okay, and we'll introduce that in the next class. And good, I have more time, so I can take more time to talk to you about these things. Do I get homeworks today? And also your homeworks are over here, graded homeworks. Again, I'll repeat for those of you who are not here, graded homeworks are here. Your grades for the homeworks are in the courseware. So please check them, make sure I didn't make a mistake in taking these homeworks and putting those grades there. And also see if anything is missing, then let me know and we can work out something to fix that. But yeah, please take your graded homeworks.
Yeah.
Yeah. Oh, I graded which? You submitted them? Yeah. Where did you put them? Ah, okay. Sorry, I must not have checked them. I'll check. Thank you. Is anybody friends with Pen? Pen, you? You're from your lab. Can you give it to him? Yes. Do you have yours?
Yes.
Oh, okay.
But not today.
Oh.